In the previous lecture, we have seen actually a brief introduction regarding the process internal conversion. We have also defined a very important quantity related to this internal conversion, and that quantity is called coefficient of internal conversion, denoted by the symbol alpha. And I have told you that actually all the informations gathered from this process internal conversion are hidden in the quantity which is called coefficient of internal conversion. It means if you want to know the parity change or the spin change or the structure of nucleus to some extent, you can gather these informations from the coefficient of internal conversion. But in the first lecture, in the introductory lecture on internal conversion, we have seen just a simple definition of this coefficient of internal conversion. But in this lecture, our prime aim is to evaluate this coefficient of internal conversion. So this is the core problem, this is the main problem related to internal conversion, and it is very important for your different examination purpose. So to evaluate coefficient of internal conversion, let us consider the two states of a nucleus between which the nuclear transition takes place. Initially, the nucleus is in this I state and its energy is EI, and when a nuclear transition takes place from this higher energy state to a lower energy state, which I have denoted by the symbol F, corresponding to the energy EF, then actually you know the energy equal to difference of these two energy levels, that is EI minus, sorry, here will be EI minus EF, not EF minus EI. So this is EI minus EF. EI minus EF is emitted, and actually when this excitation energy is absorbed by an atomic electron present in an atomic shell, then you know internal conversion takes place. The electron which gains this much energy actually gets ejected if this excitation energy is greater than the binding energy of the electron present in that shell. Okay, so let us consider the process of internal conversion. So we will neglect in present discussion previously the process of gamma decay, because you know in this condition gamma decay also takes place. But for the evaluation of coefficient of internal conversion, we simply consider that only internal conversion takes place. So this energy W, which is excitation energy, and that will be equal to H bar omega, that is absorbed by an atomic electron, and if this energy is greater than the binding energy of the electron present in that shell, then the electron gets ejected from the shell with a kinetic energy, and that kinetic energy is simply equal to this W minus BK. B is binding energy. You have studied these things in the previous lecture. Now, to find the value of this coefficient of internal conversion, let us consider that when the nucleus is in its initial state, that is before the transition, then the nuclear wave function is psi I. Okay, and when the transition takes place, the nucleus is now in its final state F, then we consider that the nuclear wave function is psi F. Now since here electron is also present and it will be also in our discussion, so we also consider what is the wave function of the electron when it was present in a particular cell. Actually our discussion here is limited to the K electron ejection. So we particularly consider that the electron of K cell gets ejected. So I have mentioned here that this ui is the electronic wave function in K cell. Okay, and when the electron will be ejected from the K cell, then the remaining system will be just like a plane wave, or you can say then the state of the system gets changed, and we consider that UF is the electronic wave function in the continuum after electron ejection. Okay. Now this electronic wave function UI, you can see this is the electronic wave function for an electron which is in K cell present. So this is just like a hydrogen-like atom. So UI will definitely have a form which will be just the wave function for a hydrogen-like atom. Okay, but as the electron is ejected from this K cell, and the ejected electron has a kinetic energy much greater than the binding energy of the electron corresponding to the K cell. So this UF may be just treated as a plane wave. Okay, so UI will have a form of the wave function of a hydrogen-like atom, and what will be the form of wave function of UF? That will be just like a plane wave. All these things for your convenience I have mentioned here. You can see that this UI will be just wave function for the H-like atom. Okay, I have already told you. And as the energy of the ejected electron is large compared to its binding energy in the atom, we therefore use a plane wave approximation for the ejected electron. Okay. So now you can write what will be these electronic wave functions. As UI, you have seen that this will be just like this will be a wave function for a hydrogen-like atom. So UI is given as 1 over root pi z over a naught whole to the power 3 by 2 e to the power minus r by a. You know, this z is actually the atomic number, and a naught is Bohr radius for hydrogen atom. A naught is Bohr radius for hydrogen atom. Okay, and this r is actually the position vector of the electron with respect to the nucleus. If you consider that here is nucleus and ejected electron at any time is present here, then this distance is actually r. Okay, and equivalently you can write this expression for UI in this way. This is pi a cube whole to the power minus half e raised to the power minus r by a. Actually here I have considered that this a is equal to a naught over z, and as I have told you that this a naught is what? This is Bohr radius of H atom. Okay, so you can write this expression for UI in this manner. And as I have told you that the ejected electron will be just treated like a plane wave. So if you consider that your system is inside a volume V, then you have seen in the previous lecture that when we write the plane wave function as a plane wave, then we have written u equal to n times e to the power I k dot r, where n is actually the normalization factor. And if you consider that your system is in a volume V, which is considered as a big box, which you have seen in the earlier lecture, then applying the normalization condition, we find the value of n, and that value of n is obtained as 1 over root V. You have seen this such type of calculation in the previous lecture. So I have directly written here that this UF will be equal to 1 over root B times e to the power ik dot r. So you can say that this 1 over root V is just the normalization factor, and actually V is the volume inside which you consider your system. Okay, and in this expression, you know, this k is what? This k is the wave vector of the propagation constant. Okay, and all these things I have mentioned it here, you can see. Now the system has two parts. One is the nucleus and another is the ejected electron. Okay, and the electron present in a particular cell. So in initial, when our system was in initial state, this was just a combination of a nucleus and an electron present in a case cell. So this is just a system combined of, composed of two parts. One is nucleus and another is an electron present in a case cell. So if you want to write the wave function or the eigenfunction or the eigenvector for this state of our system, that is nucleus plus electron present in K cell, then that state will be defined by the wave function phi I, and that phi I will be what? That will be simply just a product of psi I and ui. You know, psi I is the nuclear wave function in its initial state, that is before transition, and ui is the wave function of the electron when it was in K cell, not it was ejected from the K cell then. So the initial wave function of our system will be phi I, and that phi I will be given by psi I times ui. Now, when the ejection takes place, then again the system has two parts. One is the nucleus in its final state, that is in F state, and another is the ejected electron, which is moving away from the nucleus. So if you consider a system composed of the nucleus in its final state after transition and the ejected electron from the K cell, then that state may be defined by the wave function phi f, and that phi f is given by psi f times uf, because you know we have considered that this psi f is the wave function representing the final state of the nucleus, and uf is the wave function corresponding to the electron which is ejected from the K cell, that is a wave function for the ejected electron. So in final state, the wave function of our system will be phi f, and that will be given by psi f times uf. Now we study in quantum mechanics the transition, such type of transition process, and you know the transition probability is calculated by a famous rule, and that famous rule was given by Fermi, and that rule is actually known as Fermi-Golden rule. So if you want to know what will be the transition probability of this process, that is when our nucleus it transforms its states from I to F, what is the probability of this transition? We can find this by applying the formula of Fermi-Golden rule. So remember, you have studied this Fermi-Golden rule in your quantum mechanics course. So I am writing it here directly, that according to Fermi-Golden rule, the transition probability, this omega is given by what? No, not omega, but you say it is a small w. This is given by 2 pi over h bar times hi mod of hif square times dne. Remember it. This expression has been written on the basis of Fermi-Golden rule. Now, what are the quantities present in this equation? You can see. Actually here, this HIF, you know, this is actually the matrix element of the interaction energy due to the electrostatic interaction between the proton of the nucleus and the electron. This is the transition, this is the matrix element due to the interaction which is actually of electrostatic nature, and this interaction takes place between the proton inside the nucleus and the electron. Okay, and this dne, this actually represents the number of quantum states of the ejected electron per unit energy range, okay. So all these things I have mentioned it here for your convenience. You can see that this dne, This is number of states of the ejected electrons per unit energy interval. Okay. Now, if you consider that the electrons are ejected in a solid angle, let us consider d omega. This is the solid angle in which the electrons get ejected. Then, if you want to find the number of quantum states or number of states of ejected electron per unit energy interval through this solid angle d omega, then this is given as dn by de equal to v times me times p divided by h cube into d omega. Okay, remember it. Here actually p is the momentum of the ejected electron, and you know momentum p is equal to h bar k, you know it. So this expression for dn by de can be given as v times me into h bar k and over. And instead of h, I have written here 2 pi h bar, okay? And me is actually mass of the electron. So the number of states of these ejected electrons per unit energy interval dn by de is given by v times me into h bar k over 2 pi h bar whole cube times d omega. But this is just the number of states corresponding to the electron ejected through this solid angle d omega. But you know, electrons are ejected actually almost in all possible directions. So if you want to find the total transition probability between the two states of our nucleus, that is the state I and state F, then we must consider the total solid angle, or you can say you must integrate this result. So what will be the transition probability between the two nuclear states psi I and psi F due to internal conversion in the K cell? That will be given by this formula. You can see this will be what? This is 2 pi over h bar times this much. Okay. Now we will substitute the value of dn by de, and then we will integrate the result for all possible directions in which the electron will be ejected. Then we will get actually the total transition probability. And you know that transition probability is simply the decay constant. So decay constant, which represents the transition probability from initial state to final state. So I have mentioned inside this bracket I to f. So lambda I to f will be what? This will be 2 pi over h bar at times mod of HIF square, and mod of HIF square is here, and d omega. And the remaining factor in this expression, you can see this is me h bar k over 2 pi h bar whole cube. But why this factor 2 here? I have multiplied this result by 2. Why we have multiplied? Actually, you are considering the electron conversion in the K cell. And you know, in K cell there are 2 electrons present. So as the K cell contains 2 electrons, so this transition probability is just multiplied by this number 2. And that's why I have multiplied this expression by 2. Okay. So why 2 is here, you can see. So I have mentioned it here. You can see that here a factor 2 is because there are 2 electrons in K cell, and the integral is over all directions of the electrons. So I have multiplied by that expression by 2. Okay. Now to evaluate the matrix element, first of all we have to see that what is the perturbing Hamiltonian in this case. Actually, as I have considered that there is an electrostatic interaction between the proton and the electron. So due to this electrostatic interaction, an electrostatic potential energy will be developed, and that electrostatic potential energy actually changed the Hamiltonian. So the potential energy due to interaction between the proton of the nucleus and the electron, that is actually the extra term in Hamiltonian, and that is called actually perturbing Hamiltonian. This is just an internal interaction. So the perturbing Hamiltonian due to the electrostatic interaction between the proton in the nucleus and the electron, this is given like this H prime internal, and that will be equal to, as you know, proton has positive charge, electron has negative charge. So this electrostatic potential energy will be negative. So I have written here minus sign. And you know, if we consider that there is one proton here plus plus E charge and one electron, in fact, and they are separated by distance r, then what will be the potential energy? This will be minus 1 over 4 pi epsilon naught E times E, that is E square over R. But here we have considered that our nucleus is situated at this position, and the position vector of nucleus is Ri relative to some origin, let us say this, and here is your electron, and so the position vector of this electron with and position vector of this electron is, let us say, R, then the position vector of electron with respect to the nucleus, this will be actually equal to R minus Ri. R minus Ri. Here we have considered the origin. Here is nucleus, here is electron, and if you consider that there is only one proton, then potential energy will be what? That will be minus E square over 4 pi epsilon naught and mod of R minus Ri. This is the separation between these two. But as our nucleus contains Z protons, so you have to make the sum of the potential energy for all the protons. So the total potential energy will be given by sum of this E square over 4 pi epsilon naught R minus R mod of R minus Ri, and where the summation runs from I equal to 1 to Z. But as you know that actually the protons are not discretely distributed inside the nucleus, we must assume that the charge distribution inside the nucleus is actually continuous. So if we consider the continuous charge distribution, then actually the expression for this interaction energy will be like this. We have to write this will be equal to minus summation I1 to Z E square over 4 pi epsilon naught rho integral rho of Ri over R minus mod of R minus Ri d tau. Actually here we have assumed that this rho of Ri is the static average of the nuclear charge distribution. Okay, and actually Ri, this is, as I have told you, this is actually the position vector of the proton, okay, that is of the nucleus, and R is the position vector of the electron. Okay, now when we use this expression for the perturbing Hamiltonian, then we can find what will be the matrix element HIF. Now the matrix element HIF, you know, can be given by this expression. You know, you have studied this expression for the matrix element during your course on quantum mechanics, that this HIF is given by integral phi f star H prime internal, this is the perturbing Hamiltonian, phi I d tau. Now in this expression we will substitute the value of phi f star and phi I star. You have seen that this phi I is equal to what? This phi I is psi I times ui, and you have written this psi I remains same and you have seen that this ui is equal to what? Ui, you can see I have mentioned the value of ui here. So this ui is this much, okay, and see and at the same time you can see that uf is this much, okay. So the value of ui and uf will be substituted here. I have not exactly written that expression here. So, and phi f, you know, this is equal to psi f into uf. And uf, you have seen that this is in the plane wave form. So all these expressions for ui and uf, okay, and for this perturbing Hamiltonian H prime internal, all these things will be substituted in this equation, and then you will get that HIF will be equal to this. You can do the algebra. This will be pi a cube v whole to the power minus half over 4 pi epsilon naught summation I equal to 1 to z integral d3r integral d tau rho ri times e to the power minus ik dot r times psi f star times e square over r mod of r minus ri and times e to the power minus r by a times psi I. Actually, here the first integral, you can see here the volume element has been written by d3r, and you know r is the position vector of our ejected electron, okay. So this first integral actually extends over the coordinates of the electron, okay, and the second integral contains d tau, and this second integration over the are actually over the coordinates which occur in the nuclear wave function, okay. So first integral extends over the coordinates of electron, and the second integral actually is for the coordinates of the nuclear wave function, okay. Now, as you know that electron ejected from the K shell is outside of the nucleus. So definitely, if you consider that the position vector of nucleus is Ri and that of the electron is R, definitely as the electron is outside of the nucleus, so this R will be greater than Ri. Or in other words, you can say that Ri will be less than R, okay. So under this assumption that Ri is less than R, we can expand this term 1 over mod of R minus Ri, that is R minus Ri to the power minus 1. Actually, this is expanded in terms of the spherical harmonics. All these things we study in quantum mechanics, so I have written it here directly, that when you see that R is less than Ri, then 1 over mod of R minus Ri, this expansion is given as summation L0 to L and summation M equal to minus L to L times 4 pi over 2L plus 1 times Ri square over R to the power L plus 1 y lm theta phi times y lm star theta I phi. You have to remember it because this result has been written directly. In fact, in this expression, you know, this y lm theta phi, this is actually the spherical harmonic, and this is y lm star is also a spherical harmonic. In fact, this theta and phi are the polar angles for the vector r, that is for the nucleus, and this theta I, phi I, these are the polar angles for the electron, that is for the position vector r. When the position vector r will be Ri, in corresponding to that the polar angles are theta and theta phi. You can see this, if it is r, then this is the position of, in fact, nucleus, then if you consider that this is z axis, then this angle is theta, and when you draw a perpendicular on xy plane, then this angle made by this projection with x-axis is phi. And similarly, in case of electron's position vector Ri, we will consider theta as theta I and phi as phi I. In fact, in this expression, what is this L? L is actually called electric multipolarity, and M is called magnetic multipolarity. When we actually study the multipole expansion during this beta decay process, then these two quantities comes into our calculation. Okay. So the L is electric multipolarity and M is magnetic multipolarity. Okay. Now, the electric multipole moment for the nuclear transition from the state I to F is defined in quantum mechanics. So we will use here directly the definition of the multipole moment of a nuclear transition from its initial state to final state, which we have studied in the quantum mechanics. Actually, the quantum mechanical expression for the multipole moment of a nuclear transition from initial state I to F is given like this. All these expressions you must remember, because we are writing it here directly, and this is just a compulsion to write these things directly, because these are actually a vast concept which we study separately in other topics of quantum mechanics. So definitely you have to remember it. Okay. So something this will be not very interesting, because we have to remember so many complicated equations. So one thing may feel boring, but as you know, in physics there are so many complicated equations which we remember, but the final result when is discussed, then we actually enjoy it. So remember these mathematics you have to remember. So what I was telling? I was telling you that the multipole moment for the nuclear transition from state I to F is quantum mechanically defined as QLM I to F. This is E times summation over I1 to Z Ri to the power L Y LM star theta I phi I and psi f star psi I d tau. This is just the value of multipole moment of a nuclear transition from initial state to final state, as we study in quantum mechanics. Okay. Now, this value of QLM from I to F and the value of 1 over mod of R minus Ri, which we have actually obtained in this equation 7. When these two values defined in equation 7 and equation 8 is used in this equation 6, see here, then what will be actually the value of HIF, that is the matrix element? Now you can see. Then after substituting all those two values from those two equations, HIF is obtained as E times pi a cube v whole to the power minus half 4 pi epsilon naught. You can check it. You can substitute in that equation. I am not turning the page and writing here directly. And this is summation L0 to infinity and summation M from minus L to L times 4 pi over 12 plus 1 QLM I to F ILM. Actually here this ILM I have written for a particular integral. You can see here ILM has been written for this integral. This is integral e raised to the power minus r by a times e to the power minus ik dot r times r to the power minus l plus 1 ylm theta phi d tau. Okay. Now, as the electron is ejected from the nucleus, you know the rate in this condition, this r which is actually the position vector of the electron, this will be much greater than A, because you know A is what? A is actually related to Bohr orbit, and so R will be much greater than A. And if R is much greater than A, then this e to the power minus R by A will be almost equal to 1. Why? You can see e to the power minus R over A. You know from expansion that this will be 1 minus R by A plus 1 over 2 factorial R by A whole square plus so on. Since R is much greater than A, so in this condition, yes, and sorry, don't think about this expansion. You can understand this fact in another way. Don't think. This will be, see here, since we consider that R is much greater than A, so if we consider that R tends to infinity, if you consider, then this E minus R by A, this will be just very large, and in that condition, in the expansion, we will take only 1 and neglect all the terms. So in this condition, you can say that this R is much greater than A, so this e to the power minus R by A may be approximated as 1. Okay, and if we consider that this e to the power minus R by A is almost equal to 1, then this ILM can be evaluated by the addition theorem for the spherical harmonics. When you study spherical harmonics in quantum mechanics or in mathematical physics, then we study their addition theorem for the spherical harmonics. And in this condition, when we consider that this e to the power minus R by A is almost equal to 1, then this ILM using that addition theorem of spherical harmonic is found to be 4 pi I to the power minus L k to the power L minus 2 over 2L plus 1 double factorial YLM theta phi. Okay. So we will substitute this value of ILM now in this equation 9, and then you will get the matrix element HIF. So substituting this value of ILM in equation 9, HIF comes out to be like this. This is, you can do the algebra. This is 4 pi E over epsilon naught pi A cube V to the power half summation L 0 to infinity summation L minus M to L times I to the power L times K to the power L minus 2 over 2L plus 1 double factorial, remember, and times QLM I to F YLM theta phi. Okay. So this will be the value of the matrix element. Okay. Now, when this matrix element now will be substituted in the equation which actually defines the decay constant or the probability of nuclear transition, and if you will actually apply the integration by the use of the orthogonality and normalization condition of spherical harmonics, then you will get actually a relation for the transition probability per unit time associated with the internal conversion process. So what we have to do now? For this, we have to substitute the value of this HIF in this equation number 4. In this equation 4, you can see this is the transition probability lambda I to F, and we have to put the value of this matrix element HIF in this equation. But when you will substitute the value of HIF in this equation, you must evaluate the integral, and as I have told you, that integral will be evaluated by the use of the orthogonality and the normalization condition for the spherical harmonics. So using the orthogonality property and the normalization property of spherical harmonics, sorry, the page has been turned, but it will be just okay. In fact, there is some problem in my device, and so sometimes the page gets turned automatically. So don't mind these things. When I will actually change my iPad, then these problems will be removed. Okay. So I have mentioned here that substituting this value of HIF in equation 4, you have just seen the equation 4, and simplifying the integration by orthogonality and normalization of the spherical harmonics, we get the relation for the transition probability per unit time associated with the internal conversion process. And what will be that result? I have mentioned it here directly. You can see this will be lambda IC I12. IC here stands for internal conversion. And that will be actually resulted like this: 8me times E square over pi epsilon naught square h bar cube a cube summation L 0 to infinity summation m minus L to L and k to the power 2l minus 3 over 2l plus 1 double factorial square times mod of QLM I2F square. Okay. Now, you know, in this expression, due to the particular selection rule, certain values of L occur. Okay. So definitely we have to neglect in the calculation of this lambda, that is transition probability rate, the contribution due to the gamma decay, because you know in this process during the internal conversion, gamma decay also takes place. But if you want to know the probability per unit time of this internal conversion, then you must neglect the contribution of this QLM due to the gamma decay. So I have mentioned it here. You can see we also neglect the contribution Q prime LM for the transition probability of gamma decay of the states between the states I and F. So when we will neglect it, then what will be our result? You can see. Actually, in that condition, when we also neglect one thing here, you can see. As you know that the energy of the ejected electron from the K cell, that is equal to what? That is equal to W minus BK. Okay. And this is kinetic energy, and kinetic energy is P square over 2m. Okay. 2me, and that will be, and W minus BK. Okay. But what will be P? P is H bar K. So this is H bar square K square over 2me, and that will be equal to, and HW, you know, this is H bar omega, a minus BK. Okay. So in general, we know that the kinetic energy of the ejected electron from the K cell, which is H bar square K square by 2me, is equal to H bar omega minus BK. But if you consider that this excitation energy H bar omega is much greater than BK, that is binding energy of the electron in K cell, then this will be almost equal to H bar omega. And so from here we can find the value of K, and that will be equal to 2me omega over H bar whole to the power half. Now this value which we have obtained here in equation 14, we will substitute this value in the equation 13, and see the equation 13 here. In this equation, the value of k will be substituted here. You can see here k is present, and we will substitute the value of k which we have just obtained here under the assumption that the excitation energy h bar omega is much greater than bk. And at the same time, as I have told you, that you have to also neglect the value of the q for the gamma decay. So taking all these things under account, then what will be the internal conversion coefficient? Internal conversion coefficient, that is simply the reciprocal of that lambda. So this alpha ke of L. Here actually E represents the electric multipole moment. E is for electric multipole moment, and K represents the ejection from K cell. So after this we get actually alpha Ke of L equal to L over L plus 1 Z cube times E square over 4 pi epsilon naught H bar C whole to the power 4 and times 2 MEC square over H bar omega whole to the power L plus 5 by 2. Actually, I have not simplified the algebra. You have to simplify it separately, but for your examination purpose, you must remember these things and write directly, because when you will do all the algebra, there will be we will take a much larger time, and that will be actually just time killing. Okay. Now, this is just an approximate result. In fact, using the Dirac relativistic theory which you study in quantum mechanics, in fact, Rose found an exact result for this conversion coefficient. So I have mentioned it here. You can see the exact theoretical expression for the conversion coefficient was given by M.E. Rose using the relativistic theory of Dirac. Okay? And this expression for K cell conversion coefficient for the magnetic multipolarity M, that was actually for electric multipolarity E, and this expression is for magnetic multipolarity M. So I have written here M, you can see. So alpha Km of L, this comes out, this expression has been written directly here. This is Z cube times E square over 4 pi epsilon naught H bar C whole to the power 4 times 2 ME C square over H bar omega to the power L plus 3 by 2. Now, this is the expression which I have written here directly, which was obtained by M.E. Rose on the basis of the Dirac relativistic theory, and this expression, which is for in fact electric multipolar, in case of electric multipolarity, this we have obtained in this lecture. Now we will see what informations, main informations we get from these two results. If you see these two results, you can see actually these two results are actually valid, or they are actually in a good approximation only when this quantity Ze square over 4 pi epsilon naught H bar C is much greater than 1. Okay. And also you have seen that in this calculation we have assumed that H bar omega is much greater than Bk. You have just seen, because we have neglected the value of Bk, that is binding energy of electron in K cell, in comparison to H bar omega. So this relation will hold only when we consider or we assume that Ze square by 4 pi epsilon naught Sc bar is much smaller than 1, and the transition energy H bar omega is much greater than Bk. Then these two results will hold. Okay. Now, from both results you can see this alpha Km is proportional to Z cube, and you can also see that this alpha Ke is also proportional to Z cube. So on the basis of both of these two results, we can say that the conversion coefficients are actually proportional to Z cube. So if you consider that Z is increasing, so if Z will increase, then the value of this conversion coefficient will strongly increase. Why? Because Z contains 3 power. So if you consider that just Z is doubled, then the values of alpha will be almost 8 times greater. 8 times it will increase. So we simply say that the increase the coefficient conversion coefficient increase strongly with Z. Okay, and this is the reason that this internal conversion process dominates over the gamma decay when the value of Z is large, that is nucleus is heavier. So you can say that in case of heavier nucleus, the process of this internal conversion dominates over the gamma decay. But if the nucleus is not heavy, Z is not large, it is a small, then actually gamma decay dominates over the internal conversion. So I have mentioned it here that in light nuclei, gamma decay is relatively favored. So this is a very remarkable fact that when internal conversion will take place, internal conversion is favored in case of the heavier nuclei. But in case of lighter nuclei, the transition of nucleus from higher energy state to lower energy state is mostly accompanied by gamma decay. But if the nucleus is heavy, then it will be via the internal conversion. Okay. Now see these two expressions. In both of the expressions, this h bar omega factor is in the denominator. You can see the another expression too. H bar omega is in denominator. So you can easily say that if h bar omega will be large, then alpha will be small. So I have mentioned it here that they decrease with increasing transition energy h bar omega. It is obvious from the result. And hence transition corresponding to a small energy are mainly through internal conversion. Okay, so if transition energy is smaller, then it will be via the internal conversion. Transition during the transition of nucleus from higher to lower energy state, internal conversion will take place. But in other words, you can also say that if the transition energy is in fact large, then this process is not favored. Okay. Now, for h bar omega, if it is less than 2 MEC square, actually MEC square is the rest mass energy of electron, and if this h bar omega is smaller than the twice of the rest mass energy of electron, then the process of internal conversion increases with multiple order L of the transition. You can see it here that if L increases, but I have mentioned that this h bar omega is less than 2 MEC square. H bar omega is less than 2 MEC square. So you can see when this condition will hold, this number inside this bracket will be actually greater than 1, and if it is greater than 1 and you increase the value of L, then the value of this quantity will increase, because when you increase the power on a number which is greater than 1, then value increases. But if h bar omega will be greater than 2 MEC square, then reverse will be the phenomenon. So I have mentioned it here that if h bar omega is less than 2 MEC square, then this 2 MEC square over h bar omega will be greater than 1, And in that condition, with increase in L, the value of alpha will increase. Not alpha km, but you can also see that the value of alpha ke will also increase. So this is another remarkable fact. You can say that I have mentioned that if h bar omega is less than this much, the process of internal conversion increases because the value of alpha will increase with multiple order L of the transition. So these were some of the important facts which we have obtained from the result for alpha. I think this was not a very interesting lecture because there are so many questions in this lecture, in this concept, which I have just put it. But this is just a compulsion, because if you want to see all the calculations in detail, that will be a very lengthy process, and for your examination purpose you must remember those things. So I hope you will be not in fact you will not get actually bothered. You must enjoy and try to watch the video and write down everything, and something will be must be remembered by you. Okay.